Right, welcome back. Good afternoon, everyone. So we are starting our lecture number 10. So just one more week to go. I think I had a question from Laura about the assignment. Should we define a function to perform the script in part 2? So let me see what I wrote there explicitly. Just one second. So hopefully you guys can hear me. I'm going to share my screen just in a sec. There we go. Let me check that we have everything in place. Okay, so the question was about part 2 of the assignment. I just want to be sure to see what I wrote there. I don't think you need a function for part 2. No, it's just going to use just calls, because in principle you could create a function, that's fine, but this one will work as your main driver script. So if you decide to create a function, that's perfectly fine. If you just put the functions, calls, the commands inside the script, that will be okay as well. Okay, let me know, Laura, if that address your question. Let me know also, guys, if you have any other questions. Perfect. Check. I think we have everyone. Oh, this is here. Okay, in any case, let me know if you have any other questions about the assignment. Just as a reminder, the assignment is not due today, but next Thursday. We talked about this almost a week ago, so we decided to shift. If you are done with the assignment, of course, you are more than welcome to submit. I may take a look at the assignment submissions tomorrow or during the weekend, but officially or formally speaking, the due date is next Thursday. I think I updated that also in the website. Yes, it says May 21st, so in a week from now. The other thing is, next week I'm going to be, because the assignment is now due in a week, next week I'm going to be posting probably at least one more assignment, that's for sure. But then I'm thinking about posting 2 assignments, and then you pick one, right? So we still remain 5 assignments. We will see how much time and opportunity we have to cover topics. So for today I'm going to try. I'm not sure I will be able to cover all the material in the visualization slides, probably not. It's a lot there, so it's most likely that we will have to do it today and on Tuesday, and then depending on how much we can cover today, I can plan ahead and see if we can fit something else on Tuesday. If not, we will end on Thursday with probably high performance R, unless I heard something else about you. Okay, again, please let me know. Let me know also if you have any questions from what we had covered last class. So we ended the discussion on how to create models in R, and we started discussing some of the functions that we use for plotting. Okay, so again, let me know if you have any questions about that. Otherwise, I'm looking for the slide where I stopped it last time. I think this is it. And again, let me know if you have any questions during the presentation as well. Okay, so I think this is, so we talk about the different options, the part function, which is super powerful, and we will come back to this function, which is one of the particular functions that you need to use when you customize your plot. Okay, so the other functions I want to present to you today, among many others, is the device function. So there is a bunch of dep for device functions. So dep.new creates a new graphical window. Dep.list lists all the graphical windows. Dep.car lists the current graphical identification of the window. Device.off switch off a window. This is also used for when you have the output of the graphical output dump in a file, similar to when we were closing files. So this is also used for when you need to close a file, and we're going to see this in a second. Device set is used when you have the list of graphical devices, and then you want to switch to one particular one, or alternatively you can do device next and device previous. Now, and which equal device current basically tell you which is the current device, and then you go to the next of this device or the previous of this device. Now, these are very generic functions which basically open a window, and if you have been playing or you follow along the examples from the linear modeling class, you will notice that what happens is when you type one graphical command in R, and maybe we can demonstrate this right away. When you do, let me open one of my terminals here. If I open R here, and I'm just going to do a very quick plot just to demonstrate what I'm saying. If I do plot of 1 to 10, this is just a vector. Now what happens is R is popping up this window where the plot is drawn. So this is the graphical window that I was referring to, and the one that you control with device new. So if I do device new here, now you will see there is another window that is open, and if I do plot 1 to 102, now there are two graphical devices in my computer. The one with the original plot, the one with the next plot, and if I redo the previous plot, the 1 to 10, then it overrides that, because that is the active graphical window. And you can pop up as many windows as you want. So the idea of popping up these windows is that in some cases, if you want to explore more data, it's useful to have a bunch of them sitting one next to the other, or however you want to arrange them. Now, the reason why I mention this is because depending on what operating system you are running, depending if you are using a Mac, if you are using a Windows machine or a Linux box, there are specific ways to handle this as well. So if you're in Unix, you can use the X11 command. If you are in macOS, you can use the Quartz command, which is the Windows manager for these graphical entities. And in Windows, you can use Windows. Now, the advantage of this, so each method has its own advantage and disadvantage. The ones on the left, the advantage is that they are very generic. It works independently of the operating system. It's what we usually refer as OS agnostic. They don't care in which operating system you are. They basically bundle with the core of the operating system to handle this. The ones on the right are very operating system dependent. So if I am in a Windows machine and I try to use Quartz, it's probably not going to work. Why they exist is because in some cases they also allow you to have more features. Like for instance, if I took the Mac OS and I use Quartz, then there's a lot of nice things that you can do with a combination of keys, and you have a little bit more of control. Again, I'm just letting you know, in case that you ever see some of these commands called in scripts. My recommendation is, if you're going to develop things that you don't know where is it going to be used, or you're trying to have it like as generic as possible, use the device kind of commands versus the OS dependent. Okay, let me see. Any questions about this? If not, I'm going to show you how to create subplots. And subplots is a generic way of also creating insets, like when you have a plot and inside the plot a tiny zoom up of a region or zoom in of a region. So we're going to use a similar example as before, a vector from 1 to 100 divided by 100, meaning from almost 0 to 1. And now we're going to start using the par function. And what I'm doing here is par mfrow equal and then a vector 2, 2. So what this means is for R, it's going to divide our graphical device or canvas or a screen, graphical screen, into a 2 by 2, meaning a 4-element anything matrix or arrangement. Okay, so mfrow stands for the number of columns and rows, and that's what it means. So when I execute my first command, similarly to what we did last time, plot of x and then the sinusoidal function, it places the plot on the very up left corner. If I do a next plot, similar again as we did last class, and now specifying some parameters for this plot, it goes to the next one. If you remember, what we used to happen here is, because I'm using two consecutive plot commands, if it was just one window, it will overwrite the original one. But because now I have a grid of 2 by 2 elements, now I'm going to keep jumping ahead. If I do a next one, again, another sinusoidal function with different parameters, different colors, different title, it goes to the next one. Okay, so it starts upper left corner, move to the right, bottom, and then to the right again. Okay, and of course I could add a line command here, and then it will add that line to this plot on the bottom left corner. Okay, so that's the way to create subplots. Okay, and as I say, you can control, like for instance, you start with just one single object, one single mf row equal 1 1, then you will have one plot, and then you can change that to a 4x4, and then you can draw a tiny inset or a small inset inside the main plot. That's the way you create insets in R. Alright? Now, one of the things, any questions about this? Let me see my chat. I think we are clean. Okay, so let me know if there are any questions. So one of the other features that R has with respect to plots is that it has a variety of different plots that you can try and use. And in addition to that, there are a lot of other libraries that you can import. But let's see the basic ones here. I usually like to show you the very basic ones. I know people is very fond of ggplot. It's one of the most used graphic libraries within R and other languages. It's even Python. But I want to show you the very basic features that R has, and then I let you choose the ones that you prefer the most. So let's see a little bit of the different type of plots that are also allow you to create. So we have histograms and pi. So let's take the air quality data. I believe we saw this data set before. It's one of the default data sets. I'm just renaming it as data. And then I'm going to use the hist command. The hist command, by the way, is part of the plot MC function that you guys are going to use for the assignment. So the histogram I'm plotting there is using hist. And basically you can just pass the vector. In this case, it's the concentration of ozone. And basically it will take that, it will bind into different beings, and then draw the usual histogram. Now this function is powerful because it can also return the actual data of how the histogram was created. I can do some tiny data analysis. For instance, I can say, okay, let me know what are the bad days, defining bad days where the level of ozone was greater than 20, and then I can actually aggregate that due to the month, which are the months of the year where there were really bad days. And now this is a table, this is a command that we also saw, and now I have in which months and how many days within each month there were a level of ozone greater than 20. Let me see, I think we have a question in the chat. Okay, perfect, good question, Chenji. So AB line basically allow you to add just one straight line, meaning like y equal ax plus b. Lines basically allow you to add a line that connect dots. So for using AB line, you need two parameters to define the line, either the slope and the independent term. I think you can also give it with other coefficients, but let's say slope and independent term, so a and b in the equation y equal ax plus b. Lines, you can give a sequence of numbers, of points, and then it will connect that. It will basically connect the dots and give you the sense of a smooth curve if the dots are well distributed. Okay, so lines allow you to connect dots. AB line just draw a straight line. Okay, we're going to see probably one more example about that. Perfect. So we are looking at this and now I'm saying, okay, can I identify now the actual names of the months? And remember, there is this month name function where you can basically take the names here, which are the numbers of the month, and then it will give me that as the actual numbers. And then I can create a vector with that, and then what I can do is a pie chart. And now in the pie chart, what I have is the month where there were a level of ozone greater than 20, identified by the actual names of the months, but also representing over the total number of bad days, the distribution across these different months, actually. The other thing is that you can select from a palette of colors, a variety of different palette of colors, which colors to use. So for instance, color here is using the terrain color, and the selection of colors, because these are discrete points or colors, is given by how many elements we have in the vector result. And in this case we have 5, so it picks 5 colors from the discrete palette of colors. Again, the variety of tools that you have for R is almost infinite, I would say, because there is this R blue color package that is awesome. It defines all kind of colors. It has colors categorized by different features. For instance, it has color for colorblind people, so it's good to use those kind of conventions, for instance, when you try to communicate something for a wider audience, right? So again, it's just giving you a sense of what kind of things you could do very easily, very straightforward with the function for now. You can draw a box. I think I showed you this command some time ago. It basically enclose the graph that you have in a box if you would like to do that. Maybe you shouldn't, or you would. One of the other, any questions about this, please let me know. If not, I'm going to move into another graphical object that is one of the most popular ones, is box plots, and I call this box plot and whiskers. Whiskers are actually these kind of tiny triangles that you can use to represent that. To be honest with you, if you want, there's an interesting discussion going on with this type of plots, with the box plots. The idea of box plot is that they can give you a very quick sense of the distribution of the data. And here in the example, for instance, I'm taking again another data set from R. It's called insect sprays, where there are different categories of substances or chemicals used to spray insects, and then I don't remember exactly the count of dead insects or something like that. It doesn't really matter. The point being is that one of the things that the box plot allow you to visualize is the distribution of the data, and the discussion is that maybe box plots are not the most I don't want to say useful, but maybe accurate. Maybe that's the better way to describe this. Not the most accurate way to represent this, and instead of this, you can use something called violin plots, which not only, so basically this gives you the distribution in the y-axis, but not giving you much information about the distribution in the x-axis. So if your data doesn't have, so in this case it's categorical data, so it won't make too much sense having distribution on the x-axis, but it can be insightful to see the violin plot. So the violin plots try to draw smooth surfaces around these distributions. So again, it's an interesting discussion. You can look at some papers arguing about this, but still box plots remain to be one of the most common plots when someone performs a statistical analysis. So in this case, it's very, very straightforward to draw a box plot. I have customized here a little bit this box plot. So box plot count versus spray is what is going to put is in the y-axis count. So this is what you see here, and the spray is the spray categorical variable, the type of different chemical use. The data is coming from the insect sprays data frame, and the color is light gray. Now you are not seeing this plot in the slide. What you are seeing is the plot coming from the second line, which is the one that had the notches, and the notches are this tiny thing. It's called notches or whiskers. And what it says is notch equal true, equal true, and then the color is blue. So it had these notches and the coloring inside the box plot. And I think I have a question in the chat. Yes, that's right, Sisu. The month name is a built-in function in R. Yes, that's right. You can use it. It should pop out right away. So if I show you month.name, is right there. Okay, and basically it's not even a function. It's a data set. It's the set of names, and what you can do is slice this with whatever number, so you can pick that directly from there. Okay. What else? Yeah, no problem. Oh, bar plots. This is the one that I just added a few months ago because I have a student doing microbiome studies, and apparently is used a lot in microbiome, so I decided to add this. But this is the typical plot that you can create even with Excel and so on, so it's nice to see that R allow you to create this and also allow you to control a lot of things. So for instance, the example I'm showing you here, not only the distribution of colors and categories is given, but also, if you notice, the width of each of the columns, and this is represented here. So here I created 4 samples for artificial samples that can represent measurements of different categories, or it can be different experiments, or whatever you want to think about. And now the bar plot is the function that allows you to create this type of plot, but this type of plot are quite generic. So one thing we can control is the height. And what I'm doing here is, you can see the cbind function. So I'm creating a data frame actually, and I'm saying x is given by the sample divided by sample 1 over the sum of sample 1 times 100. So what I'm doing here is basically taking these samples and normalizing these values in percentage representation. So it's exactly the same values as I defined here, but I just decided to normalize to 100. So that's why you see all the colors reaching the same height, and basically the inner samples distributing across them. Now the other thing is beside equal false means they are not going to be clamped together, so there is a tiny gap between them. Sometimes for visualization purposes it helps, but this is where I control the width, setting the width equal to, in this case, 1 for column 1, 2 for column 2, 3 for column, and you see the width increasing. Now this, which is set by hand here, could have come from any other observation. So it means that in principle I have the feature to add one more dimension to my representation by just changing the width of each of the columns of the bars in the bar plot. The colors also are selected by hand, 1, 2, 3, 4, 5. Remember, can interpret a color by names like black, red, green, blue, or by color, and that's exactly what I'm saying here, and that's why each column star or each bar starts in black is 1, then goes to red, green, and blue. Legends, that's the legend that you see right here, and then the arguments of the legends, where do you want to place it? Okay, I could have put top here, and it will show here top in a better position than what I decided to do here. The names, X, Y, Z, are the names of the columns in the data frame, and that's where these ones come from. Okay, so again, a nice and useful way to create another type of visualization of plot. Okay, heat maps. Another one that is super popular is heat maps, because again, heat maps allow you to have, it's what we will call, or I will call, in particular for the assignment that will come next week, it's a higher dimensional representation of data. And the idea here is mostly it's used when you have, how to say this, more higher dimensions arrays like matrices, tensors, those kind of things, or relationship between different variables, like multidimensional relationships between different variables. So in this case, and again, I'm using another data set, so we can see that we are exploring a variety of the data sets included in R. In this case, it's the empty cars data sets. This is a data set that contains information about cars in the United States, the different brands of the cars, and then different features of the cars. And actually, you can see here this in the heat map. You can see the brands of the car or the models of the cars, and then the specifications. So, for instance, the number of cylinders, if it was an automatic or manual car. I think this, the weight, the number of gears, and so on, a variety of different things. Now, one thing that the heat map function requires for work is that it has to be the data laid down as a matrix. Okay, so we need to place this as matrix function in front of the data frame. Then what I'm doing here is I'm creating, so instead of using the predefined color scheme from R, I'm creating one based on the rainbow color scheme. So that's a color map or a palette, if you wish, from R. which is given by the number of rows and number of columns. So one is going to be applied for the number of rows and the other for the number of columns, and it starts at 0 and goes at 2.3. So that gives you basically the different shades of colors that you will have. Now the heat map, similar to the histogram function, allow you to return and capture information about the heat map, about how it was created, how it was basically created, as I say. Not only that, but also you will see these things on the right. This is like phylogenetic trees, if you wish. It's called dendrograms, and what it does is it tries by looking to similarities in the different features to arrange the data and say, oh, these are closer, this can be a small cluster. So there is some interesting features going on, and all that can be captured in a variable. That's why I assigned this to HB. Now the heat map takes one argument for the data, and then it takes multiple arguments for different customizations. So color comes from the CM colors, and that's the color representation inside the histogram. These RC and CC are the color representations on the rows, relationships between the different branches in the dendrogram. And that's why row side colors and column side colors are given by RC and CC. Okay, you can control the margins to give more space. You can put labels on the X and Y axis, and you can have a general title by main, and that's exactly what it says here. Okay, the backslashes here are necessary because I want to use quotation marks here. So because quotation marks are surrounded by quotation marks, if I don't put these slashes, then I will think, okay, this is finishing my text, and that's why I need extra slashes here to say, oh no, this is part of the actual text that is going to compose my title there. Now, one thing to warn you is the heat map functions is quite powerful, but it's very basic. You will see that heat maps with no more professional features, but heat maps that require more fine-tune, let's put it that way. People don't use the heat map basic function for now, and instead use packages like heatmap2. There is another p colors, I believe, p heatmap, sorry, that allow you to create more customizable heat maps. For instance, one downside of the heat map function is I cannot put here a color bar specifying which are the actual values associated to each color. That's a pity, but that's something that is not present in this function. But by using packages like heatmap2 or pheatmap, that is easily fixed. Okay, just to warn you, just to show you the very basic functionalities that are offers. Okay, any questions about this? I'm giving you a very high level tour about the different functions, different ways that you have to create plots in R. So that's the goal here. I think I mentioned most of these functions. The plot functions, we saw that the lines and AB lines, we just clarified that. The hist function, the bar plot function, pi, a strip chart similar to the bar plot but allow you to do stripes, box plot, dot chart, mosaic plot. This is similar to the mosaic plot that we created when we start exploring the linear modeling topic last class. And there are others, right? Like for instance, there are these ones that are more like tools, I would say, like arrows. This is what allows you to actually add error bars to an existing plot. Axes allow you to basically take full control of how the axes are drawn in the plot, and this one we are going to see more in detail in the examples about professional plots. Box, you saw this one when I draw my pie chart. If you want to basically enclose a given box, you can set box. This one, believe it or not, is useful in combination with axis and with the function plot setting axis to false. We are going to see this again in an example, but this is why I mentioned this. These, believe it or not, are things that you will have to take care of if you decide to go and create a script that does a plot that can be part of your publications in a journal. Legend allow you to create a legend. So in many cases R1 put a legend by default, so you need to activate the legends. Text allow you to add text to plots, points allow you to add specific points to your plot, and then polygons allow you to draw polygons. So you will say again, this sounds like kind of silly, why I will do that, and I can tell you an example. By using polygons, I was able to create a function that allow you to do some kind of confidence interval around a mean value. So if you saw the exercises I posted, there is one exercise I think is asking you to create a function to compute a moving average function. So one I think that sometimes is useful to have is to have a moving average indicator and then have a confidence band surrounding that, and that you will actually achieve by using polygon. Now, if you have experience and you have used other graphical libraries or packages in R like ggplot, that's exactly what ggplot does. Now, you can, I personally, I think ggplot is a great package, by the way, but I personally don't really like the type of plot that ggplot generates. The reason is, there are a couple of reasons, but the reason is I can see a paper and in seconds tell you this plot comes from ggplot. Nothing wrong with that. It's just it's a matter of personal taste, kind of. So I prefer to have full control, and that's why I usually like to show you the very basics functionalities that are offered. Other people that just jump into ggplot, don't worry about ggplot. We are going to discuss ggplot when we talk about Plotly, and I tell you a little bit about ggplot there. It's a great tool and a lot of people use it, so it's nothing wrong with it. It's just, as I say, it's something, it's a little bit of personal preference, if you wish. Okay, any questions about this? And I'm going to move now into two-dimensional and three-dimensional plots for a second, and then hopefully we will be able to cover the professional plotting part 2 today. Let me just check the chat, because sometimes it's supposed to blink when there is a question, sometimes it doesn't do it. I think we are fine. Okay, so let's talk about two-dimensional and three-dimensional plots. The first example I have for you is a contour plot. And a contour plot, what basically represents is, imagine you have a three-dimensional object, like a surface, and now you are taking cuts in a fixed position in the vertical direction of that surface, and basically when the cuts intersect the surface, you project that into the horizontal plane, and then that's how you create a contour plot. What is the advantage of this? Well, you are able to basically reproduce, capture information of a high-dimensional object into a one less dimension, basically a two-dimensional plot. And that is what we're going to do here. So I'm going to define an n value as an integer that will represent how many cuts I'm going to take, in this case 27, and then I'm going to define what is called a grid, a Cartesian grid, basically coordinates for the x and y direction, going from minus 4 pi up to 4 pi with 27 values of this. Okay, so x and y has that. Then I'm going to represent what is just a function. So I'm going to, here, what we are going to reproduce, just to let you know in advance, is a Gaussian bell. It's a two-dimensional Gaussian surface, or two-dimensional Gaussian bell, or two-dimensional Gaussian distribution, or normal distribution, as you wish. So my x squared value is going to be given by a matrix, which is repetitions of x. So I'm going to have x going from minus 4 pi to 4 pi, and then I'm going to take x squared values, n times of this, with n rows. Okay, and similarly with y squared. The only thing is I'm going to take the transpose of that, so instead of having x, I'm going to have y. So that's why I'm taking the transpose. And this is how you create the contour. It's very straightforward. You use a function called fillet.contour. You give the coordinates in the xy plane, and then you give the function. This is in this case, it's a two-dimensional function. It's a three-dimensional representation. It's a two-dimensional function because it depends only in x and y. It's the exponential of minus x squared plus y squared divided by, this will be over sigma squared, a given value 60. And what you can see here, this is the straightforward representation that I will give you, is the different contours that you will see. You actually, if you can zoom, you can see the different contours and the different colors, and each color represents a value. So you should be able to reproduce the shape by basically saying, oh, this point here, which is at 0, 0, has a value of close to 1. And that is what you expect with the Gaussian, right? The only thing is now is an xy representation of the Gaussian. We're going to see how it looks in 3D in just a second, but just to give you a sense of how the contour looks like. Okay, I imagine most of you are familiar with these. Typical cases when you see contour plots are for atomic levels, or for instance, if you're looking at maps in cartography, in geography, sorry, you see the different colors representing the different altitudes of the surfaces. That's the typical contour plots that you will see. Anything that is like that that has one more dimension can be broken down to projections, basically cuts and projections of these values. You can of course decorate the plot with titles for the X and Y axis, and of course you have more control on this function. There are a lot of arguments, but I'm just showing you again one way to represent data, and a lot of things that you can tweak with this function. Okay, now let's see how this actual plot looks in 3D. So there is a function called pairs from perspective that basically takes exactly the same arguments from the fillet contour one, X and Y. So remember, X and Y are filled as vectors in a matricial form because they're representing our grid. So for each X I have to have m values of Y. That's why we did that. And this is the exponential, the Gaussian again. Okay, and this is kind of a mesh representation of that, or sometimes called wireframe, and you can rotate that. So same thing, but now I rotate a little bit, two angles, theta and phi. So one is the tilt in the vertical direction, the other is the rotation around the vertical axis. And you can put a title in your set axis called my Gaussian, for instance, right? You can also give some shade to the representation, so this gives you kind of a source light and allow you to distinguish a little bit better than before. It's just a nice touch sometimes. Okay, but that is how you will represent these 3D objects. All right, any questions about this? Again, let me quickly check the chat, because sometimes there are questions and it doesn't allow notify. Okay. There is one more tool I want to show you, because you know what, R doesn't have many ways to represent 3D data as a built-in, and for instance ggplot doesn't neither. So there are a couple of libraries that covers this point. This, the Scatterplot3D, is a good one. It's robust. It has been around for a while. There is another one that is super neat because it allows you to do interactions. It's called RGL. I usually don't include that because it has some tight dependencies with hardware, meaning that sometimes it requires OpenGL, which is a library that you have to install in your system. It's not an R library, it's a system library. And sometimes if you don't have that, it won't work, or if you don't have a powerful CPU, it won't work. But if you are able to install it, I strongly recommend, because it allows you to do very nice things. In addition to that, Plotly, which we're going to see at the end of this series of slides, allow you to do some very cool 3D representation. So this one, let's take it as a static kind of 3D representation. It's very straightforward to use. Remember, you will need to install this library. This is not part of the basic R packages, and of course you need to load the library. I'm going to start a new device here, and I'm going to create a bunch of vectors. So X is a sequence from -10 to 10, every 0.01, so a good number of points there. X is a consign parameter, a function given by the set parameter. So this is a parametric curve, what we usually refer as, and set is going to be the parameter. X is given by the cosine function of the parameter, Y is given by the sine function of the parameter, and of course when you plot this in the XYZ plane, it's nothing else than a helix representation, or helicoidal representation. So the way to reproduce this plot here is to use the function scatterplot3d from the scatterplot3d library, provide X, Y, and Z, and then a bunch of options. So highlight 3D equal true, it basically colors code the points. So this is plotting actual points, and it's telling that depending on the height to change the color. The color of the axis as you can see, can be changed to blue, for instance. So the box representing the axis is in blue. You can set the color of the grid. So the grid here only in the XY plane is light blue. There is a main title here, and PCH is the size of the points used to represent the data. Okay, so this basically represents a helicoidal equation or parametric equation, as you wish. Now there are way more things that you can do in 3D scatter plot. So for instance, I'm going to take the same data set that we saw last class for doing the linear model, so the trees data frame. Excuse me. And what I'm going to do now is, instead of using just the scatter plot 3D function as it was in the previous example, I'm going to assign the result of this to an object, a variable called S3D. And the reasoning for that is then I can manipulate this object and add more things. So if I do a scatter plot 3D of the data frame, now the data frame has three variables, if you remember: volume, girth, and height. Remember, and we were actually fitting, what was that, volume versus girth, I believe, or height, but I think it was volume versus girth. It shouldn't matter much now. Now, by doing this command, what I will have is this representation of points, okay, the points itself. I'm including type equal edge. Type equal edge, what does is it draws a line from the horizontal plane up to the point. And sometimes I find it useful because it allows me to basically identify where the point is located in the plane, so I can basically go back and say, oh, the height in this case was between 85 and 90, while the girth was between 20 and 22. Okay. Highlight 3D equal trees, so each color of the points is proportional to the height. That's basically what it's doing. Angle, basically shift a little bit the angle of the representation, so you need to play with that. Scaling Y also plays a little bit with the scaling in the Y-axis. PCH, as we saw before, is the size of the point, and then the main is the title. Now, I have this object S3D, so I assign this to this object. So now what I'm going to do is, from this object, this variable, I'm going to use what is called a member function. And this is getting very object-oriented. I think I mentioned at the very beginning of our course, OR is an object-oriented language. We don't use it as much because we do mostly functional programming. That's what we usually do when we create our functions. But we have the feature of dealing with, when the libraries allow you to do so, dealing with what is called properties of the objects. And what we are doing here is, from the S2D object that basically inherits properties from this function, is to use a member function. This is called a member function. So the $sign here, which we usually refer to as columns in a data frame, is used as a function associated to this particular object that was created from this function. And in this case, what I'm going to do is I'm going to add points to the scatter plot 3D. Okay, so basically it's adding points to the representation. Okay, there is one more interesting thing that we can do. Is, if you remember, we did something like this in the linear modeling example, but now I'm going to model this, the volume, which is my vertical axis, as a linear combination of girth and height. Now, if you remember, when we were doing the linear modeling, we were creating a line, a linear model of volume versus girth. But now, because I had two variables, what I'm going to create, and because I'm giving just linear dependencies, is a plane in the XYZ space, in this case girth, height, and volume space. So my volume is going to be represented by variations in the girth and height. And in this way, this represents a plane in this three-dimensional space. How I do that, how I represent this plane, and this is how to draw the plane presented here, is to use from the object S3D the plane 3D function now instead of the points 3D function, and then I just assign, in the same way that we did with AB line, I just assign the equation, the result of the fitting of the plane, and then I'm giving a parameter here to say inbox the plane in a solid line, otherwise it represents as dashed lines. But that's the way to create a linear model in a three-dimensional space and the representation associated with it. Okay, any questions about this? Okay, let me see the chat. How are we doing? Okay. Again, I found Scatterplot 3D is a simple library compared to other more sophisticated libraries, but it allows you to do three-dimensional plots, or plot representation, cursor representations, and simple objects like plane representations. Okay. Okay. Before jumping into professional plotting. Now, most of the things I have shown you so far are for visualizing things in these pop-up windows that we saw at the beginning with the device new function. The question is, okay, if I'm representing my data, I want to put this in my presentations, my slides, or my papers, how I say this, and I'm just telling you from the get-go, taking a screenshot or capturing the screen is never a good idea. The reason why is when you do that, you are capturing bits, and bits, the way to represent bits is not always the best way to represent plots. What you want is, especially for your publications, is to have a format that is vectorizable. And what I mean with that is when you have a format that is vectorizable, and we are looking at basically two types of file formats there, PDF and EPS, or PS for PostScript if you wish. This means that you can scale out your plots. So this turned out that this is the way that we basically represent information in graphical objects. Two basic ways. One is to represent the graphical information as a matrix, and imagine that you have a matrix so large that each dot represents a point of data, and you can color that point of data and so on. If you think about that, look at the screen of an old TV basically, and you will see a pixel, what we call a pixel basically. And the problem here is if you take that picture and you stretch it, your pixels will get magnified, and you end up with an effect called pixelation. Now, an alternative way to represent the graphical information is, instead of putting pixels like in a matrix representation, take exactly the same information, but now represent the position of the pixel with a vector. What is the advantage of this is, if now I stretch my vector, I know how to mathematically transform that, and the resolution of my image, of my graphical information, won't change. It boils down to that, how, or the two ways to represent information. So, with that picture in mind, formats like BMP, JPEG, PNG, TIFF, all these are what we call pixelizable, or these formats that don't store the information in vectorized ways. So R has the ability to save images in BMP, in JPEG, in PNG, or TIFF, and that's how you will use it. But also has the feature of saving the images in PDF. So I would strongly recommend to save your images, especially for publication purposes, in PDF. And this is going to be part of your professional plotting set of tools. I saw a question, I will go just to it just in a second. The other thing that is important is in many of these formats you can specify the size and the resolution. And again, this is important when you are preparing plots and figures for your publications, because nowadays most of the journals, not all of them, they have very strict criteria and conditions for accepting your figures. It has to be of a given size, and it has to be at least 300 or 600 dpi in resolution. Okay, and that's how you specify. The last thing before I look into the question is we need to use the divide off command. I mentioned this at the beginning of the class, for closing the file. Okay, in the same way that you will use a closing file statement for your netcdf files or any other files, you will use this for closing the files. Okay, I saw a question or something popping up in the chat. Just a second. From Jennifer. Okay, how will you say if we want to edit them in an Illustrator? Okay, good question. I'm not really familiar with Illustrator. I imagine that you can open vectorizable formats like PDF, EPS, or PostScript, so I will save it as that. If Illustrator does not handle vectorizable formats, and then you may need to save it with BMP or JPEG or PNG. Maybe there are libraries, as I say, I'm not really familiar with Illustrator, but maybe there are libraries that allow you to say in a format compatible with Illustrator. I don't really know that. But what I'm going to mention is thinking mostly like you will prepare everything that you had to do for the images to go to your journal within R, and I will show you most of the tricks that you probably use, and maybe something else. As I say, I'm not really familiar with Illustrator. I try to just prepare my plots in a whole script and functions that it's all a goal is to produce the plot. So if I had to, I don't know, it happens to me many times when I submit a paper, then the referee comes back to me maybe in a month, 2 or 3 months sometimes, and asking, okay, you know what, change this plot, or this plot could be better if you do this or that. Then I just go and change my script and I can reproduce my plot. Otherwise I find myself trying to recreate the plot all over again. But I'm going to tell you more about that when we see the examples of the professional plot. Okay, so I don't really know about Illustrator. If it reads PDF or EPS, you can save it with R. If it only reads PNG, you can also save it. I just warning you that in many cases you will end up with these pixelized images if you want to modify the size. So something to bear in mind. Okay. Alternatively, instead of using the commands I showed you before, if you also want to display the plot in the device, you can use this sequence of commands: device copy to PDF, or device print, and specify a PostScript device. And there are others. Usually what I do, to be honest with you, is I create a script that generates my plots, then I source it in R, I see how it looks in the terminal, and then I save it into a PDF. So one thing to warn you, and you will see this in a second, is what you will see in the terminal, not exactly what you will, how it will look in the PDF. So there are some subtleties that we need to be aware of and take care of. And that's why the next session of the professional plotting part. Okay. Let me see if we have any questions. And I'm sorry, probably my answer was not what you were looking for, Jennifer, regarding Illustrator, but I don't really know much about Illustrator, sorry about that. So some suggestions and comments and recommendations when you're dealing with professional plots, or what I mean with plotting for professional scientists, is plots that are aimed to a journal or a professional journal, a reference journal. Some things you may know, I'm going to go very quickly through this. So label everything, access lines, feeds, data, that is everything in the plot. Put units in your axis, especially if you have color bars. Use legends when appropriate. Adjust the font size. This is particularly important, especially if you generate tiny figures in a two-column format. Do not put titles in the main plots. This usually is reserved for talks and not for papers. Do not use crazy colors. I will show you an example in the next slide. And this is very important. Try to take advantage of the real space of the plot. Try to make the plot, the data fill the plot. Otherwise, you are wasting space. Some few more suggestions. You will need to set the image size, as I was mentioning, and the resolution as requested by your journal. Do not use bitmap or stroke fonts. The reason was the one I was mentioning. Instead, use these vectorizable images and true type fonts. Try to avoid bitmap and JPEG formats that are usually accepted by journals are EPS for encapsulated PostScript or PDF for portable document format. Do not leave a bunch of white space around the white plot. That's something that usually R does. For instance, people using ggplot doesn't need to deal with this because ggplot take care of this. But if you're using the basic functionality of R, you will need to take care of that. And this is the final comment, and the one that I'm going to ask you to create in the assignment is create a script in R or any other language, whatever is your favorite language, whose sole purpose is to reproduce the plot for your paper. Okay, so for each plot, I recommend to have a particular script that if you have to change something, if you have to tweak your data or access, or you have new data coming from the lab, you can execute that script, and then you boom, reproduce the plot or create a new plot in a matter of seconds. Okay, again, some suggestions, some recommendations, as I will say. This is what we don't want to see in a professional looking plot. This is what you won't see in a journal, in plots in a journal, in a paper presented in a peer-reviewed journal. You won't see these crazy colors, you won't see these backgrounds, you won't see axes where you cannot read the numbers, where are not labeled, where you don't basically understand what information is being displayed or what is the information sent. Okay, again, simple and silly thing, but sometimes these shocking images capture more than what I can just describe in words about what to do or what not to do about professional plots, right? Many colleagues of mine, and sometimes myself included, when reading a paper, we're very cheap on the way we read papers. We read the title, we read the abstract, sometimes the authors to see how, who is writing the paper, and then you jump ahead to the figures. And the figures somehow, I had this idea that the figures of a paper should tell you a story. So by reading the figures, reading the captions of the figures, sometimes describing what the figures tell you, you should be able not to completely and fully understand the paper, but to get a sense of what the paper tries to communicate. So again, it's my personal point of view here, but the thing is it has some truth to something there. Richard, funny enough, it looks like a retro kit. Yes, I completely agree with Richard on that. Yeah, if you are used to the 80s, 90s type of coloring programs or drawing programs, that's exactly the type of background they will use. Yeah. So let me see, we have few minutes actually, so you know what, I don't think we will have enough time to cover this in detail, and I really want to go into the detail, but I think what will happen is whatever is left from professional plotting, animations, which I think is a fun topic, especially if you have data that can be animated, either because it's time data or because you have multiple dimensions and you can convert your dimension into one of these parameters that construct the flow of the data. And the interactive plot we are going to cover on Tuesday. Okay, so we don't rush, we have enough time. There is no need to rush because, as I say, assignment 5 is going to be posted probably for Tuesday because it will fit very nicely with this topic. And then we're going to have some fun with the interactive plot. And then by the end, which is next Thursday, a week from now, what I have in mind is to cover high performance R, unless I heard anything else from you guys. So if you have a strong feeling that you will prefer to see something like model diagnostic, I think I have someone mention something about that, but so far it's just one person. So unless I have like a little bit more of boost on that direction, or you want to see something more about machine learning, I think we're going to stick with high performance R, which I believe is a good thing to see, especially in a course like this that is supposed to be aimed to programming. So we are going to go back to some basics in programming and some basics on how the computer works with performance. So I think it's a good idea, but I would like to hear about you if you have a different opinion or you would prefer to see something else. And I think that's mostly what I have for you guys today. Again, remember assignment 4 is due next Thursday. We will have one more assignment as far as I can tell. I don't think, yeah. So it will be assignment 5. I think I'm going to post it on Tuesday, but no pressure. You will have 2 more weeks to work on it. Okay, so if you are still working assignment 4, it should be okay. No pressure there. All right. And I think that's what yeah, I don't want to go into the details of it. So this is one of the scripts I'm going to show you. I'm going to show you a second script. So 2 examples of how a professional plotting script should look like. And of course, I'm not doing the modularity part here, so that is what I'm going to ask you to do for the assignment. And I just want to warn you, I usually like to see a little bit, we haven't had the chance, honestly, in this course to interact much in the usual way you will do in a course, but I really would like to see a little bit of what you guys do for your own research. So what I usually ask you to use is your own data. If you don't have your own data, some data that is representable of or representative of what you field does, or any other data that you find interesting that it can produce a nice looking plot. Okay, but that we are going to talk a little bit more on Tuesday. Again, I'm going to remain in the chat for a few more minutes if you have any questions about either the assignment or the material we covered today, or the course in general, or anything else you want to discuss. And otherwise, I will see you on Monday. So Monday we still have the office hours, especially if you need to work in the assignment, or on Tuesday for the lecture. All right. As I say, I'm going to stay in the chat for a few more minutes. Have a nice weekend, everyone, and I will see you next week.